Welcome back, everyone. Now, let's move on to our final panel discussion of this year's Tokyo Forum. Space exploration was once a symbol of national pride and power. But today, private enterprises are entering the field, transforming outer space into a new economic frontier. Will activities in space lead us to redefine capitalism itself, or will capitalism reshape the future of space? In this session, our expert panel will examine the rise of space capitalism from ethical, institutional, and scientific perspectives. Our moderator is Professor Miyamoto Hideaki. He heads the newly established Center for Space Resources and Innovation at the University of Tokyo. The center serves as a new international hub for advancing the science, technology, and policy of space resource utilization. Professor Miyamoto has contributed to numerous planetary missions, including Hayabusa, Hayabusa 2, Hera, and Kaguya, and is the principal investigator of one of the instruments for NASA's Artemis 3 mission, the first human return to the moon in over half a century. So Professor Miyamoto, the floor is yours.
All right, thank you, Miyamoto-san. It is a great honor for me to serve as the moderator of this session. I'm sure that some of you guys are wondering why we're talking about space in a panel in the rethinking of capitalism. So let me start with a little bit about the background of why we think that space resources is a very good, provide very good viewpoint to think about the fundamental of the current economical system. This is the population growth from back in 10,000 BC to current. The sudden change increase in the population is mostly comes from the Industrial Revolution, which is 250 years ago. Let me provide some concept of Earth calendar here. Let's say the 4.5 billion years of Earth history compressed into a single year, which means January 1st, Earth born, and we are now at the end of the very day of December. In this sense, human emerged at 11:30 p.m. on December 31st. So the Industrial Revolution, 250 years ago, which is a long time ago, but for Earth, it is just 11:59 p.m. on December 31st, 58 seconds, which means it is a 2-second surge of prosperity. Do you know that about 7% of humans who ever lived on Earth are alive today? And each of us consumes about 6 liters of oil equivalent energy and 35 kilograms of materials per day. So Earth's resources are being depleted, and actually environmental pressure are increasing. So can we still afford to imagine that unlimited growth is possible? Let's look at outside Earth and space. Do you know that over 200 spacecraft have explored more than 100 bodies across the solar system? Out in space, we find almost unlimited frontiers and resources. This image shows the several solid bodies in the solar system in the same scale. Earth is the biggest, and you can see several very fancy bodies in the solar systems. And humanity already possesses the technology to reach those worlds. However, bringing resources back to Earth remain far from economically feasible, even though using them in space can be. Then we have a very important, interesting question. Legally and ethically, are we ready to exploit space resources? We are living in this place. This is, of course, Tokyo. Our civilization create a lot of dense buildings, cars, and machines. most of these rely heavily on iron. And in Japan, we import the iron from the other side of Earth. Remember the environment of Earth. If you put iron, it will be oxidized. So we can import the oxidized iron from the other side of Earth. Then we have to chemically reduce it to use as a metal. That means we need to put a lot of power energy to do that, which means we put a lot of impact onto the environment of this planet. So imagine if there's an alien, they watch us, and they might wonder, why do humans keep damaging fragile planets just to sustain growth? Why not look outside and use materials that are easier to use in space without placing further burden on Earth? Or why not shrink civilization into a sustainable steady state, no expansion, minimal consumption? So these questions focus us to reconsider the foundations of our economic system. So perhaps this is the moment. This is the moment to rethink capitalism. Okay, so this is the background. So now, if we want to talk about space resources, then we must begin with a scientific understanding of what materials are existing in space and what are reasonably accessible. So in this story, it is my great pleasure to introduce Professor Erik ASPHAUG from University of Arizona. Erik is internationally recognized as one of the most influential planetary scientists. His theory of formation of the moon, he's contributed to reveal the nature of asteroids and comets. These works have significantly changed our understanding of the solar system. So we're truly privileged to have him here and to share his insights. So Erik, the floor is yours.
Well, thank you so much. And the youth group's a tough act to follow, I think, so I'll do my best. And what I wanted to leave you with is a sense of what's out there. And I know that most of you are not astronomers, most of you are not planetary scientists, and but everyone knows about science. And I think one of the reasons I'm showing this picture here at the start is that I'm of the age, I grew up in the Apollo era. The Apollo mission launched and landed on the moon in 1969, and about a fifth of the world watched it, about a quarter to a third of the population that was grown up watched it. It was a very unifying event for the world, and then we sort of took it for granted. We took space a little bit for granted. This image is by the Clementine orbiter, which was, after a 20-year hiatus, the United States had not gone back to the moon. And what's beautiful about this picture is you actually see 6 planetary bodies here, in a sense. You have the Saturn, you have Mars, you have Mercury, you have the sun over the limb of the moon, you have the moon itself, and then what's lighting up the moon on the right-hand side of this picture is the Earth. And it's all this environment that is left to explore. And when I was listening to the talks today especially, and also yesterday, the word planet kept coming up, and the boundaries of the planet. And what are we doing in an economy that's bounded up against the edge of a planet that, as Miyamoto-san was saying, is in the process of severe degradation. And I do believe people would look at us from another star system and say, what are you doing? So what I want to tell you about as a preface to the other talks is just a little bit about where we are and where we can go realistically, and some of the impediments that face us. For example, the fact that distances are vast, especially once you get beyond the Earth-Moon system. And the energies to get there are vast, and space is an environment that's not empty, but it's full of lethal radiation. And And then what do we as fragile humans do in this space? How realistic is this space economy? And so this divides into the science concepts of biology and anthropology. What do humans need? And we've addressed these today and yesterday in the forum. You know, what do we need as humans on the planet Earth? We all need sunlight, energy, heat, air, water, soil, food, shelter from radiation, which we take for granted. We have an atmosphere above us that blocks cosmic rays, and you don't have this on the moon. And we need also dignity. And I maintain we need landscapes that are preserved for future generations. We don't want to degrade the environment around us. On the other hand, we're in the age of AI, we're in the age of advanced robotics, and so we need to wonder, what do robots need? Which I think will become increasingly extensions of ourselves in some proxy manner, especially as we explore the solar system. Robots, they don't need what we do. They need energy and power. They need durability, redundancy. If parts fail, they can't heal themselves. They've got to have some redundancy. They also need radiation resistance, autonomy, and intelligence and communication. The other scientific concept is that of the geology and the geophysics and the physical reality. We all watch space movies where we, go to other star systems, or we zip out to Jupiter. Many movies are more realistic than others. Few numbers are useful. Round trip to the moon is not that hard in some sense. I just flew from US to go to the moon is just 50 times farther. It's not that far away. You look up in the sky. The Greeks knew exactly how far away it was, interestingly enough. Asteroids that whiz around in near-Earth space, which I'll talk about in a second, those might take months to years to get to, until we might have the capability to capture one into orbit around the moon or possibly around the Earth. And then to go farther to Venus, Mars can be years of a journey, and then to get beyond to Europa and Titan, where there's an atmosphere that's Earth pressure atmosphere, or Europa that has an ocean equal in volume to Earth's ocean. That could take decades. And so I'm going to focus on cislunar space, as we call it. This is, if you think of gravity as a well you have to get out of, so to climb up the stairs to the top of this tower, it takes work to get up there. And to go out of Earth to get to the moon or get into space takes work. You do work against gravity. And that's what this figure represents, this surface. And the moon sits outside of Earth's gravity well. To get out there, you need big rockets. That's why the emphasis on these big, huge motors that can propel you into space. Even though they're nearby, they take a lot of effort to get there. But once you're out there, you'll notice this little yellow line on the left here talks about communication time. That's another kind of a time scale, which is, in addition to the effort it takes to get somewhere or the time it takes to get somewhere, how long does it take to communicate? And so the students spoke about isolation. If you're an astronaut living on Europa, for example, you'll wait hours for someone to hear what you have to say and for that to get back to you. If you live on Mars, it might take tens of minutes. If you are on the moon, it would merely take seconds. And so this sense of what humans care about, being able to say, hey, how are you doing? And then have someone communicate back to you, that's a very significant issue of distance. The robots might not care so much whether they have to wait a long time. If you've read Kurt Vonnegut novels, you'll know about this. This diagram here is sort of a subway map of getting out there, and all it really says is that it takes, how much work does it take to get to these different places? To get from the surface of Earth into orbit around the Earth is the biggest jump. That takes a lot of effort. That's why these rockets are huge to get into low Earth orbit. And then beyond that, you can have smaller and smaller propellant to get to the point where you can go to LEO is low Earth orbit, GEO is geosynchronous orbit, where the communication satellites are, and then you take these steps getting off to other places farther and farther into space. So I'm going to talk focusing on the moon and on asteroids for the last few minutes here. The resources on the moon are various kinds. I'm going to put on my glasses so I can read my own slides. But the main interest right now for the moon is the discovery of ice on the south pole of the moon, deep in these craters. And you know, you see sort of rosy pictures on the left. I think these are really excellent to frame what life is going to be like operating small research outposts on the moon. But the fact is, everyone out there is being dosed in high levels of radiation right now in that image. And so you have to have places where you can shelter yourself. So in the previous image of the bunker, if you want to be a lunar living in a lunar city, I hate to break it to you, but you're going to be spending a lot of your time living down under the ground in a bunker. And so the idea of being on the South Pole has a lot of interest because you have access to water where you can do, have potential building supplies. And the other nice thing about the South Pole of the moon, because it rotates with low obliquity, that is the South Pole and the North Pole kind of point north and south relative to the Earth and to the sun, you can find places that are in permanent shadow, which is where the ice is on the moon, and those same places are very close to places that are in permanent sunlight and that are also in permanent line of sight to Earth. So you can call your friend and hear back from them in seconds, and you can have solar power and you can have resources. One thing to think about for lunar settlement or lunar economy as we think about expanding into space and in the context of rethinking capitalism is, do we want to do to the moon what we've done to the Earth? And the answer, I think everyone agrees, is no. We should do some lessons of what we have done and how we approach economic development on a planet, and what does it mean to preserve. And this is the Apollo 17 tracks. Those will be there for 1 million years. And so the things we do on the moon will be there for 1 million years. So we want to think carefully. Asteroids, very briefly, they are full of all kinds of interesting minerals because they never melted and differentiated. You're saying, where's all the metal on the Earth? It's down in the core of the Earth. And that's why gold is precious, because most of it's in the center of the Earth. It went down there with the iron core. And so on asteroids and primitive meteorites, you have little bits of copper. I'm giving an analogy of here from a thin section of a meteorite. And there's another meteorite down below that's a more primitive meteorite. There's water, organics, sulfides, lots of precious materials, exotic materials that might be useful. Apophis, which you've probably heard of, which will be flying past the Earth in 2029. Apophis alone has about 1,500 tons of copper in these little grains. If you had some processing ability to grind down that copper. I like to say that asteroids are sort of everybody gets one kind of prospect for capitalism and development in space, because there are about 1 million kilometer-sized asteroids in the main belt. Not kilometer, 100-meter-sized and larger asteroids in the main belt. And so, and in near-Earth space, there are fewer. And then space is also a place where the sunlight is eternal. When you're out in the, away from a planet, there's nothing shadowing you. And so you have infinite quantities of solar power, and you have the ability to run, for example, server farms if you were to build them in space, and you wouldn't have the kind of impact. Less familiar resources on asteroids. This is the picture of the OSIRIS-REx mission as it was collecting its sample, and it's sped up by quite a factor. I don't know exactly, but it's moving in at 5 centimeters per second, which is about as fast as my hand's going. And so it came into the surface, and its surface just parted ways, and it had to thrust to get back out of the surface. The point is, this material is very easy to manipulate. There's lots of it. And when you talk about radiation shielding and what's going to protect you from the cosmic rays, you might be able to cover your spacecraft in this stuff and build yourself a ferry boat that goes back between Earth and Mars, for example, where you could be living inside and not have to worry about radiation damage. So going beyond, there's no question that we can go beyond cislunar space given enough time and enough resources to do so. Mars, of course, has river channels, river networks from the past. It has abundant water resources. And then asteroids like Ceres in the main belt has ice-covered surface and briny volcanics that have erupted onto the surface. The JAXA MMX mission is going to be exploring Phobos and Deimos in the Mars system. That might be stepping stones where you get to the halfway point where then you can operate perhaps robotic mechanisms on the surface of Mars. And then you can dream about going beyond to planets like Titan, which has an atmospheric pressure similar to what we feel in this room, but a temperature of only about 100 Kelvin. So that's the landscape, and I'll just hand it off from there.
All right, thank you very much. It's a great summary, a beautiful summary of what we know about solar system, especially the near Earth valleys. So building on this foundation, we now turn to how these scientific realities connect to resource utilization and emerging business models. So it is my great pleasure to introduce Professor Angel ABBUD-MADRID. Angel is one of the world's leading figure in space resources. He is the director of Center for Space Resources at Colorado School of Mines. It's a global hub for research, education, and industry engagement in this field. So we are fortunate to have him here with us today. So Angel, the floor is yours.
Thank you, Miyamoto-san. Konnichiwa, annyeonghaseyo. It is a great pleasure to be here at the Tokyo Forum to talk about how resources beyond Earth not only will enable future space exploration in the ways that we have not seen before, but also very related to this forum, how it's going to increase the number of commercial activities and how it can start integrating space into our global economy. And the way I'm going to do this is by answering 4 fundamental questions. The why are we looking for resources beyond Earth? What exactly we're talking about resources that are outside our planet? How is that we going to go about identifying, extracting them, and utilizing them? And who is interested and who will benefit from this? So let's start by looking at the why. And let's start by looking at resources on a planet that we all know very well, which is our planet Earth, in which resources have been the driving force behind exploration, and they have become an integral part of our lives, our society, and our economy. And to see how this can help us to understand about resources beyond Earth. So let's start by going 100,000 years ago and meet our ancestors, the Homo sapiens, that were able to go beyond Africa to Europe, to Asia, to Oceania, looking for basic survival. They were looking for water and food. But in the process, they developed technologies that allow them to live in ever more extreme environments, to live off the land. 15,000 years ago, it was the first economic revolution, agriculture, that allowed humans to finally settle in a place and be able to store energy and food. Once they were there, the soil that they had is the one that they used for building first huts, villages, then towns and entire cities. A perfect example of this is the small village, fishing village of Edo that then became the largest metropole on Earth, which is Tokyo. Then in the 15th century, it was about looking for resources for trade. Now it's economic value. There is silver and silk and spices when we started traveling across oceans. In the 19th century, it was about searching for oil all over the planet, oil that still is our main source of energy. 10 years ago or so, it was about rare earth, which are now fueling our renewable and communications industry. And just a few years ago, it's lithium that is electrifying everything around it. So as you can see, resources have allow us to explore every corner of our planet, have allowed us to live off the land in ever more extreme environments, and they have become the main engine of our technological society and of our economy. So what happened when we started going beyond Earth? Why did we go out, and what is it we found? Well, first, it was the competition between the 2 superpowers of the day, the Soviet Union and the United States, that were looking for technological superiority. But once the space race was over, we kept going, mostly to gather scientific knowledge. But in the process, we realized that space had value, that could be useful to us, that had actually economic value. And that's how we have become extremely dependent on everything we do here on Earth, on our space assets. This started with this small satellite called Telstar that started giving us communications between continents. And what Telstar was able to do is utilize the very first resource in space, and that is just location, the view from above. That's how we got global communications, weather forecasting. We can pinpoint every location of the Earth with extreme accuracy, and we can monitor the health of our planet from up above. Not only is the first resource, but telecommunication satellites is the only economic use of space at the moment. It's a $630 billion a year industry that is predicted to go into the trillions by several studies. In fact, 2 months ago, China stated that we may go into a $1 trillion economy by 2040. Now, in order to go to those levels of investment, we're going to have to go beyond just the location above Earth. But here is where it's important to understand that even though we have unlimited resources in the solar system, it's important to understand that our resource is an element or feature that has value by its utilization. If not, it's just an element of scientific curiosity or interest. It has to have a value. In terms of capitalism, it has to be able to give you a profit and be useful for that. And there are 3 steps that one needs to have in order to go after resources in every planet or even Earth. And these 3 important steps are the following. First, you have to have a recoverable resource. That means you know a resource with enough geological, scientific, engineering, but also economic, legal, and environmental certainty that you know that you can go after that. In the mining and the oil and gas world is what's called a proven reserve. Once you have that, you have to have a technology to recover it. And third, as important, if not more important, you have to have a customer. If nobody cares about this, you can have as much as you want of an element, it is not a resource. So what I'm going to do is going to go through these 3 steps. First, the what, the how, and the who. So let's take a look at the what resources are out there after Erik gave us a tour of how to get to all these places. Beyond just the location of our view from above, the moment you cross the atmosphere of Earth, you encounter an environment that is very difficult to find here on Earth. You have ultra-high vacuum, you have low gravity, and you can use that to make products that have much better properties than here on Earth. Let me give you some examples. Here is astronaut Norishige Kanai from the Japanese Space Agency that is testing how to make fiber optics in low gravity with better quality than here on Earth. Just at the beginning of this year, a company came out to look at how to make implants, bone implants and nervous systems in low gravity that also have better properties. Another resource is just solar energy that we have used since the beginning of time. And that is good not just to power a spacecraft, but imagine what we can do if we can collect that energy in outer space and bring them down to Earth in microwaves and can give us plenty of energy. This is a concept called space-based solar power that started about 40 years ago, but has gathered attention lately. China has come up with an idea of how to do this. They're actually testing systems, how to collect and transmit energy. In fact, Europe is taking this seriously, and as part of this 2050 net zero strategy, they predict that about 15% of the energy of Europe in 2050 will come probably for space solar power. And these are what's called the intangible resources. For more concrete ones, one needs to travel to destinations. And Professor ASPHAUG already told us about what type of resources out there. On the moon, you can tell there's minerals, there's all sorts of metals. You can have water for humans or for propellant. You can have oxygen. We have soil for construction purposes, ices that come from asteroids, and also volatile that comes from the solar wind that has implanted on the soil. We can go to asteroids, different types that have carbon, have water, even platinum group metals. And even go to Mars, where we have gases like carbon dioxide. And the moment you have carbon, you have methane, hydrocarbons, plastics, and everything that we use. And these are just natural resources. Believe it or not, we have human resources in space. And that's actually all the trash that we have sent into space for 60 years that we need to get rid of. But instead of burning in the atmosphere, why not recycle? This is a sort of resource and use it for metals and construction. The question, once you look at all of these resources in just one slide, you may be asking, well, what resource is more valuable? In what should I invest? This is a tricky question. Is it in the long term or in the near term? Are these resources to bring to Earth or actually to do in space? In the near term, bringing resources to Earth doesn't make any sense. We have plenty of those here on Earth, unless we start digging too deep or spending too much power or making a lot of environmental problems. There's no point on that. The whole point about resources right now in space is because you can utilize it in space. Why? Because then we can live off the land, just like we did here on Earth. Instead of having these rockets that have to spend so much energy and so much cost to do this. It's what we call in this field in situ resource utilization. So now that we know this, which resources are more valuable? First of all is water. Water that not only you can drink, but you can split into hydrogen and oxygen, the most energetic rocket propellant that you can find. And the moment you have propellant in space, you lower transportation costs, you can open up all sorts of activities. This is exactly what happened with oil on Earth. That's why we call water the oil of space, because it's going to open up all sorts of activities that we want to do in space. Other things that are useful is just the soil that we can use for construction. And we can use it for 3D printing metals, for spare parts or tools. Now we go into the how is that we're doing, making this possible. We're going to follow the same way that we do in the mining industry. We follow what's called the space resources value chain, from prospecting all the way to selling a product. So starting with prospecting and exploring on the moon, we've been doing this for decades. We know that in the surface of the moon, there's plenty of resources that can be of use. In fact, just this year, there has been a couple of missions that ended up on the surface of the moon with drilling and excavation systems. Korea already has a mission called Danuri that is looking at water on the poles. Japan, in a couple of years, is going to have a mission called LUPEX that is going to have a rover looking at water on those permanently shadowed regions. On asteroids, we heard that we've brought samples from Hayabusa 1 and Hayabusa 2, and Professor Miyamoto was one of the co-investigators that now we have in our hands what type of resources are on these asteroids. Mars, we have been going there for many years, and also the moons of Phobos and Deimos. And also Professor Miyamoto is involved in a mission called MMX that will come back with samples from these asteroids to tell us what's in there. And Japan is collaborating with the US and India and other places. Next on the value chain, once we know about the resources, now we do the mining and the processing. And there are already projects going underway to see how is that we're going to extract the oxygen, the metals, the water. Then you move into manufacturing and construction. How are we going to use the soil to make first a base by the end of this decade, and eventually we're going to have a settlement on the moon. And you can start seeing the analogies as of Earth. Remember how Edo became into Tokyo? That's exactly what we're going to have on the moon. Not as large, but similar to this. And finally comes the economic part. How are you going to distribute and sell? And here it's important to know that customers exist at every level of the value chain. And not only that, business cases can operate also at every level of this. And so finally we come to who is doing this type of thing? Who will benefit? Who is interested? Well, first of all is governments, space agencies. The moment you lower cost, that will make much better for them to go explore space. 15 years ago, it was just NASA, the American Space Agency, that was interested in this. But in 2016, one of the smallest countries in the world, Luxembourg, saw the value, the economic value of this, and started looking at how, and conducted a study with PricewaterhouseCoopers, and started looking how much would it cost to do this, who's going to benefit, how many jobs can you create. And once this happened, the field of space resources and the interest exploded. Now you have Russia, you have other European countries, Canada, India, Korea, you got China, you got United Arab Emirates, you got Australia, and you have Japan. In fact, the Japanese agency is going to start collaborating with a center that is now here at University of Tokyo, the Center for Space Resources Innovation, and Professor Miyamoto is the director that is going to get involved in this type of missions. Not only is governments, it's launch providers, companies like United Launch Alliance that can see the benefit of saving by having propellant made in space. Lockheed Martin started thinking about landers that can actually utilize resources on the moon. You have Boeing and Northrop Grumman creating the fuel depots in space. And you have now the billionaires entering, offering how to give rights to companies or space agencies so they can get to the surface of the moon and the like. And it's not just the large aerospace companies. There are more than 120 companies, from startups and entrepreneurs, from middle-sized companies to large companies that have been doing resources on Earth, that are now looking into space, that are involved in all aspects of the value chain. Who's going to explore, who's going to extract, who's going to collect, all the infrastructure that will be needed, power, transportation, and the like. And so you can see now that the interest is from governments and the private sector. And one question remains. Is this legal? Can companies and countries actually set up operations and extract resources? Are there any international treaties that tells us about this? And not just is this legal, is this fair? Is this going to be only 2 or 3 countries that want to be able to enjoy this newfound wealth? Or are we going to have to rethink capitalism in space so that all countries and all humanity can benefit from this? This is what my colleague, Professor Aoki, is going to talk about in a few seconds. So thank you very much. Arigato gozaimasu. Kamsahamnida.
Thank you very much. So this is the perfect transition to our final perspective, law and ethics. So I'm very honored to introduce Professor Setsuko Aoki from Chiba Institute of Technology. Professor Aoki is one of the world leading authorities on international space law. She served as the chair of the UN COPUOS LSC, a legal subcommittee, which is the United Nations body responsible for shaping the legal framework of global space activities. So she was also the first woman and the first Japanese scholar to serve in their roles. So we are truly privileged to have her here with us today. So please, Professor Aoki, the floor is yours.
Thank you very much, Professor Miyamoto, for your very kind introduction. So I will talk about 10 minutes on legal and ethical aspects. And here, well, the right side of your slide shows 5 United Nations treaties on outer space. Only 5 treaties have been made up until now, because everything has to be decided on consensus. So when the last of the treaty, the Moon Agreement, was made in the Committee on the Peaceful Uses of Outer Space, well, it's under the General Assembly. Well, when it was made, COPUOS members, Committee on the Peaceful Uses of Outer Space, is abbreviation is COPUOS, member states, 47. That was the end of the possible building of the consensus. Today, we already have 140 members, and next year, well, another several would join to the COPUOS. So it's very difficult to make some legally binding norms from now on. Having said that, the first of the treaty entered into force in 1967, the Outer Space Treaty. This says categorically what can do and what cannot do. And Article 2 says outer space cannot be appropriated by any state, even if it's, well, a part of the outer space is occupied. Article 2 of the Outer Space Treaty is very simple and short. So, and what it says is outer space cannot be appropriated, owned by states. And, well, it doesn't say anything about private persons, but by interpretation, private persons, natural persons, well, companies, all these things are included. But the problem for today is there is no reference. No reference is made on space resources. So it's not clear, it's vague. If you are the party to the Moon Agreement, this is clear. Moon Agreements prohibits any, well, states or any private persons to claim the property rights or ownership of space resources. It's clearly prohibited, but for the Outer Space Treaty, it's vague. International law for today is decided on territories, place. So different territories and different rules are applicable. So for national territories, so like Japan or Korea or, well, China, or so by the demarcation of the frontier of the country, different rules could be applied. And Antarctica has a very special rules. Well, today, well, I would omit about that. And there are 2 territories which are relevant to the space resources exploitation and well, utilization and also well, owning them. The first is well, international area, like high seas. It cannot be owned, appropriated by any state, but the usage of it, well, utilization is in principle. Utilization is free for well, any countries. And common heritage of mankind, this is a new addition to the territories. So here, occupation or appropriation is prohibited, nor is allowed the free use. So rule is there. So it has to be used in accordance with the rules made by an international organization or international regime. Then, well, how it's translated in outer space? For state parties, which are only to the outer space treaty, outer space is like high seas, international areas. You can use it in principle, well, as you like. It's in the realm of the freedom. But if you are the parties to the Moon Agreement, how to use it is also decided. Free competition, first come, first served rule is denied. So the Moon Agreement is the first, well, treaty of relating to outer space that denies capitalism. Free competition is clearly denied there. Oh, sorry. On Earth, there is a place like, well, outer space for the parties which belong to the Moon Agreement. That is called deep seabed. Deep seabed is, well, it's not a very precise definition. Deep seabed is a soil and subsoil of the high seas. And there, well, it's believed the precious metals are, well, there. Then, because it's very important, and if it's, well, free competition is there, only advanced states could exploit everything. So developing countries were very much concerned about the situations. Then a treaty was made called Law of the Sea Convention in 1982. There, in that convention, there is an international organization called International Seabed Authority. That organization decides how to exploit, how to own resources of deep seabed, and which should be allocated to all humanity. It's very, well, difficult one. So how to allocate the proceeds of the precious metals of deep seabed to all humanity? So still, that subject of international law is states. So to allocate them the proceed to be given to, especially to developing countries. So very exquisite and complicated rules for getting a license to mine resources of deep seabed was decided. So when natural resources are there on the deep seabed, it belongs to all humanity. But when you get a license from the ISA, then a country or a private person can get it. And the moment it's extracted from the deep seabed, the ownership is in hand of the one who mined. So even if, well, natural resources is there in the place of called common heritage of mankind. Still, there are ways to get it, but the conditions are very severe. So green arrows there, it's very severe. And well, the miners have to pay lots of licensing fees and have to give lots of proceeds to developing countries and everything. So this is not well, only reasons, but today, no exploitation of natural resources of the deep sea bed is conducted, just exploration, just prospecting. So this is one of the problems that if, well, you have very noble goal, and if competition is denied, that it could be an obstacle for healthy development of the industry. So about space resources, so about the moon, the countries which are parties to the moon agreement, it's just only 17, just 17 countries. For them, the similar regime, international organization would be made once the exploitation of the natural resources on the moon would be possible. But about the other countries which are parties only to the Outer Space Treaty, which are 116 countries as of today, or well, not exactly. Some of the countries which are the Outer Space Treaty are also the parties to the Moon Agreement. So about 105 countries are only to the parties to the Outer Space Treaty. Then the regime is really vague. What happened since then is, well, still, the international society decided to talk about, to construct some kind of frameworks, which may be a light one, not so difficult, not so well severe one, which may be like the Moon Agreement type. We don't know. But since 2017, how to, well, explore, exploit, and utilize space resources in outer space has been discussed. And the working group is already made up. And so if there is a working group, in-depth discussion is possible. And it is expected that in 2027, maybe it's 2028 or 2029, well, the first recommendation, first set of recommendation about the regime, it's called regime, but it's, well, kind of recommendations, would be made as a General Assembly resolution. General Assembly resolution is just recommendation, but recommendation to all countries which belong to the United Nations means 193 countries. Outside the United Nations, well, there are lots of discussions. Well, one of the more capitalistic discussions are made in the Hague Working Group. And they made 20, well, called building blocks means 20 recommendations, and which are submitted to the copies of the United Nations. So it's one of the elements of the discussions. So, and so the essence of the Hague Working Group's result would be also included in the resultant United Nations General Assembly resolution if it's successfully made. In the meantime, there are two political commitments. The first one is very well known, the Artemis Accord. Its signing started in 2020, and today, as of today, already 60 states show the commitment to it. 80% of the provisions of the Artemis Accords are just an, well, borrowing, reflection of the Outer Space Treaty. But for instance, Section 10 of the Artemis Accord says, well, the countries which signed the Artemis Accord would make national state practice about state practice and to promote and to proceed new rule of space resources exploration and utilization. It doesn't say extraction or mining. It says exploration and utilization. A little bit of, well, it's conservative and conservative expression. But, well, state practice would make new rule. Oh, sorry. I'm very sorry. I took too much time. But there are another. There is another, well, framework which made by Russia and China. Its guidelines not clearly released to the international society yet, but both of them frameworks released as of today, the Artemis Accord and ILRS parts. Both are the reflection, both are mostly reflection of the Outer Space Treaty, and that isn't really the, well, foundation of the international society. There are some countries which made national laws on space resources exploration and exploitation, and well, also ownership. And the reason these countries made law is, well, the countries have the obligation to ensure that their national, their private parties would act in accordance with international law and also their respective national legislation.
Okay, Professor Aoki,
yeah, sorry, I took too much time.
So yes, so the national law is important for the keeping the profits. So since we are a little behind the schedule, so let me go just straight to the important questions. The Professor ABBUD-MADRID already raised this question, and Professor Aoki also mentioned about the difficulty to answer this question. But so, who should benefit from space resources? Could you please answer quickly, maybe from my help?
I think, and according to the treaties, all humankind has to benefit from that. Obviously, that is very broad, and it may not happen at first. Maybe some countries will do this, but hopefully, once they start developing the infrastructure, everybody can benefit. It's like the global positioning system. You know, it was developed by a country, but now everybody uses it on your phones. You know, you have access to all of this. So I think everybody probably will benefit from what we can do in space.
Even though we're using the space resources out of Earth, but still it's a benefit for everybody on the surface of Earth.
Yeah.
Yeah. So that's a good point. Yes, please, Erik.
Well, I think you know, people are skeptical because there are humans on Earth who have more wealth than whole countries, and so who adheres to these treaties? I think when we think about how we move forward, I like to look backwards a little bit at what the space programs means to thinking as a country. And you mentioned that it was a source of national pride. You know, who can do this? Who can land people on the moon? Who can be the first sample return from an asteroid? And then it shifts now to a forum where, you know, there it's we. And I think I look at Apollo, I look at Hayabusa as, you know, we all did this. And I think when it comes to resource development, I think I have some skepticism, you know, that it's going to be we. Or is it going to be, you know, me, the first trillionaire who does this? And so I think we need to maybe revisit some of these modes of the treaties to apply in some more global context, but that's way outside of what I know about.
Yeah, that's easy to understand, but how about Professor Aoki's viewpoint?
Well,
Yeah.
from the international law perspective, it's easy. It says, well, for all countries and all humanity.
Sure.
But well, in reality, I think it should be at first the scientific community.
All right, that's very interesting. So then I have another question actually. Should capitalism be redesigned for space or using space resources? Okay.
Just like the young people said in the previous session, capitalism is here to stay. I mean, with us every day. And whatever we do here on Earth, we're going to export it. Humans are going to export everything. It may feel like space is somewhere else, but no, it's going to happen. So I think capitalism is going to be there. But given the challenges of accessing space, there's a chance of collaboration. If you're going to have a base on the moon, everybody will have to have power, communications, and you're going to have to share it. And then, obviously, everybody will have to, each country will profit from that. But I think there's a room for collaboration, but capitalism will be exported to space. Let's just hope we do it in the right way, after we have learned all of the things from Earth.
Yeah, absolutely. Erik, you have any?
Yeah, I think it comes down to what's it worth to you. Like on the moon, probably being able to breathe is the most valuable resource in the world for a human. And you know, you could have all the gold in the world or an oxygen tank, and I think you'd know which one to pick. So I think capitalism defines the value of these resources, but I think the ability to move resources from place to place, oxygen from Earth to the moon, suddenly it's very valuable. Helium-3 on the moon, bring it to Earth, suddenly that's very valuable.
Sure.
And so I think we need to think in capitalistic contexts for all of this. But what I would love to see is we preserve this, you know, we sense of doing all of this.
Yeah, we do that things. Yes, that is important. Professor Aoki, do you have any comments on that?
It depends on the definition of the capitalism, and the
Yeah,
competition aspect is well, it's important, but well, already, well, international law is not made by the capitalistic concepts, and if we learn a little bit about the Moon Agreement, it's more for the system to allocate the proceeds of the economic proceeds to all countries and all humanity. So we have already principles, but we don't know how to do that. Procedures. So procedural aspects should be made from now on, and it's modified capitalism. It's important, I think.
All right, thank you. We still have a little time, so we have a lot of young students. So final question to you guys is, like, imagine like in 2050, for example, what is the best shape for space economy? Or what things you can do, or what we have to do to make everything better in shape in 2050?
Okay. Well, I want to leave you, especially the young generation, with a optimistic view. It may seem at some point that what we have done on Earth we'll do in space, but what resources can do for us, it's quite incredible. It not only will increase the number of scientific knowledge that we can get, but the number of commercial activities. Imagine once we start opening the whole solar system, there's a lot of possibilities. The key thing here for all of you that are going to be involved in this is that let's do it in a very technically effective way, but also do it in a fair, in a responsible, and a sustainable way. And what I mean by sustainable is the 3 pillars of sustainability. Let's do it economically sustainable. This is where capitalism comes in. Environmentally sustainable, but also socially sustainable. And I think that's the key for making the most out of resources in space.
Oh, that's a very good comment to the young people. Erik?
Yeah, I really think we need to appreciate the point that there's in situ resource utilization. I think when people think about, what are we going to do in space? We're going to find an asteroid, we're going to take the gold from the asteroid and bring it to Earth, and suddenly we'll all be billionaires. It's not going to work that way. It's going to be the things we do on Earth that are, server farms, for example. I was on sabbatical in Norway for a year, and all these places up north are being filled full of server farms because it's cold, they have water, and they can pump out data. And if data is the economy, build the server farms in space. I mean, if that's where we're being driven in this AI-based future, or being able to do activities in space like manufacturing, medicine, things you can do in microgravity. I think the idea of taking the most pollutant-based industries into space is very appealing to me.
Yeah, well, first phase of the circular economy is, I think, firmly established. I'm very optimistic.
All right.
Thank you very much.
Good, Setsuko.
That's a great conclusion, actually. All right, thank you very much. So I think, thank you very much for the stimulating this session. We have to conclude this session. So once again, I'd like to express my deepest appreciation of the great panel members, and also the people, everybody here, to engagement throughout this session. I hope this session contributes to a broader conversation about the rethinking capitalism and how humanity should shape its future beyond Earth. So thank you very much.
Thank you very much. Thank you for taking us into space and teaching us the significance of going into space and maybe the rules and the sense of collaboration that need to be put in place with the rise of space capitalism. Thank you very much.